Bismillahirrahmanirrahim. Hello everyone. In this video tutorial, I'm going to model and analyze an eccentrical brass in Abaqus software. For simplicity, I have already analyzed and completed pushover analysis here. The structure has a length of 5 meters and height of 3 meters. The length, which we called for eccentrically brass, we call link element, which is between two brasses. That's 1 meter and 2 meters right side, 2 meter left side. The cross section is I section with compact elements, which is 400, 400, 20, 20. There is 400, 400, 20, and the height is 3 meters. The brass element is a box section, which is 200, 150, 12 by 12. We applied a 3% drift displacement in this direction, and we got these results. So now we can go to pushover step 1. In the first step, we don't have any hinge properties or any large deformation. So in the second, it will begin to the life safety region. That means the structure will start to deform or damage in this area. And the second, in the next step, no, not any places, and the later we will the damage will occur in these brasses, and it's finally changed to the first floor and this beam. Yes. So finally in the first floor we will go to the collapse, and we can display the static pushover curves. So this is the static pushover curves. So until 180 millimeters displacement, so the structure will go to collapse. But here we can get the most important parameters based on ASC 41. Here we can see the yield displacement is 60 millimeters, and the yield shear force is about 3000 kilonewtons in this region, almost in this region. But which I snapped, which is the maximum, is about 4600 or 4700 kilonewtons. But after the first part of the the brass is damaged, the other remaining parts will go to the ultimate area, and it will get this maximum resisting force with a maximum 105.6 millimeters displacements. So we have done already in Abaqus. For simplicity, I used beam elements, and it's also available to use shell elements and solid elements. So I'm going to take a new eccentrically braced. Okay, I have saved this and I'm going to take a new one. I took already, set a directory in the same place which I already saved. Here is going to draw my frame, eccentrically frame. Shell element is also good to do, but it takes a little time. For simplicity, I used wire, and it's about B1000 3D planar deformable. Now here I can start drawing the first boundary columns, and let's see, this is center to center 3000, and the height is, sorry, it should be 5000, and the height is for 2-story 6 meters, and going to draw a line in the midpoint of this line. Then I can delete this part. So this is our frame. Also, I can delete this also, and this frame, this beam, and I'm going to draw to here, and I want to make a measure that should be about 2 meters. So this is 2 meters, the first part of the beam, and the second we want to have the length. Take the line and again to somewhat here, and then here. Next, I'm going to measure this one. It's also 1 meters, and this is the remaining is 2 meters. Next, I'm going to delete this one, this beam. Delete and make a copy of this using this function. Copy. Sorry. Select. Now we should take a point, and this is the center of the midpoint of this. So the frame beam column is drawn, and next we take the line again from this point to here, and from this point to here, which is the eccentrically braced system. And now I can draw the same in the first floor. So this is done. The modeling is completed. The next we're going to define properties. We can check our materials. We used FY50. So FY50, I can unlock the model to copy these properties. Modify, and this property is the elastic modulus. This is megapascal, where we're using the same megapascal. Create called FY50. The first is elastic, Control V, and this is Poisson ratio 0.3. And next is plastic properties. We want to have the nonlinear properties. Copy, paste, and it's P0. So next is the ultimate. We also can find, if I go to here in internet, I can check. Let's see FUY steel strain properties. Sorry, FUY 50 steel properties. Now we can see we can get the elongation here. Here is also, but I'm going to see one of them. Yeah, here is the tensile strain. Yeah, here 50. Yeah, this is grade 50, and it's about 21%. The minimum elongation is 21%. So I can add this elongation, copy this ultimate strength, and paste. And here is we can take 0.21. So 21% the plastic strength. The next is we have beam and columns. So we should define what we're using beam elements. So we have to use define some profile. We can column, that column is 400 by 400, and this is 20 by 20. So it's our height section. Quickly, we give the center of axis is 200, so we become 200. The height to the light is 400, and 400, which is the flange, bottom flange, and the thickness in the flange wave the same. So, okay, this is for column, and next is for beam. Called beam height is 400 times 500, 400, and 15 the flange and 10 web. The same, there should be 250, and there should be 500, there should be 400, and bottom also should be 400, B1, B2. The thickness 1 is bottom flange 15, top flange 15, and web should be 10. This is T3. Okay, and the next one is box or HSS, which is 200 height and 150 weight, 12 by 12 thickness. This should be a box here. We give the A is height 200 and it's 150, and this uniform thickness 12 millimeters. Now we should define some section we called columns. They should be beam, using beam, and here we should select the profile and same material using 3.3 for portion ratio. And another section we called beam, the same procedure using beam section for portion ratio 0.3. And the next is the rest. This is also beam section and using HSS, which is 0.3 portion ratio. So now the section is completed. We are going to define this, assign this section to the frame. Okay, and this is columns, and we're going to select beams. This is beam or beams, and now the time for brasses. So this is brass. Next thing is we should apply orientation or assign orientation. Here is our orientation. Select all beams. This is what we're gonna see, which is the direction 2 is in this side and direction 1 is in that side. So if I go to the 3D, now we can see. In profile, we can go to the column and edit. So this is direction 1. This is direction 1, which is going that side, and direction 2, which is going this side. Quite good. And again, assign for beams that direction 2 should be top. The same we have done here. And for brass, the direction, if we check that I should be in direction X, so I'm going to check this should be direction 1 should go to the X. So I can give here 1 and 0 0. Direction 1 is in the X, so quite okay. We can go to assembly and we apply to the assembly here, and we have next is I'm going to take this point to the 0, so which is the center. I'm going to see here view assembly display. I'm going to activate the rendering. So now we can see the cross section is completely assigned in the right direction. Next is we go to create a step. This is a step model. Step into push over using general static. We can use as much as one, but I want to use 104,000 because later I will do a cyclic analysis as well. So I'm going to activate, and for any sort of I can activate some automatic stabilization if there is an convergence, so that can solve my convergence problem on, and it can be about 10,000, be 0.05. Give a very small number that can handle your problem, and it's be maximum 20. And the next is we want to give a smooth curve that should be use the approximate numbers. So into exactly unit 1, and also output should be approximate. So we select the pre-default, and next is we want to go to again to here assembly of the rendering to create a seat. I'm going to create a seat displacement. This one I'm going to use it's caps lock. So this one, this two top of the roof, and this two, this one. One was top, one top of roof, and the second is here. So I'm going to select it. So what was that? I'm going to create called this roof. Continue taking this point Okay, and next is create called this. Here we should give first floor here. Okay, and the next is I'm going to create one more thing. Create called base. So the base is this 2 point. Base is 2 point, and I'm going to the tab. I'm going to U1. U1 pushover, which is going to take the displacement set using the roof, top of the roof, and using every x units 1, and output should be in approximate time. So what we want to take the history output is U1. So this one is also, if you want, we can create, but if you don't want, that's no need. The second is going to create RF from the pushover that should be set to base. So it's 2 floor because it has different base shear, and here is different base shear. So we want to take the base shear from the bottom of the structure, set base, and here is in every unit time, which should be the same in approximate parameters. So we want to take the RF1 in direction 1. Now we go to the interaction is no need. We don't need any interaction. We go to the load. We have a load in the top of these 2 nodes, which is 150 kilonewtons. I'm going to apply this load here called date load. This date load should be applied we should apply this load in one other step. It's okay. We can apply in this pushover, but no, we should apply in another. So I go to the step. This step, I want to edit this step to 1 second, and here is take 1 and 0.1. So very slowly we want to, and also we want to rename it called gravity analysis. So gravity load. And next we're going to create another one. This is called pushover. So this is pushover 1500. Two is going to be 0.5, and it's going to be 1e minus 15, and it can be 20. Okay, and here we have 2 output, and here is we want to change this to the pushover. So I'm going to write, and I'm going to write, so it's okay. It's better. So now go to load again, and this time we want to apply date load in a gravity analysis. So it's a concentric load, this point and this point. So this point should be in a negative 100. So we're using millimeters, Newton, and you're giving 1000, 150, 1, 2, 3. This is 150 kilonewtons. And the second is we are going to give this displacement. Sorry, I'm going to use base fixed using the initial part, and it can be, we can select base, these 2 points, and use the encoster. Good. And the next is we have two displacement. One is here and one is here. We want to apply the 3% of the height of the structure, which is the 3% drift. So now this is 3 meters. So the 3% will be about 90 millimeters. And for the second top floor roof, it will be 180. So I'm going to apply 90 millimeters here and 180 in this place. But this roof, it means in the same time it should push here and here. Otherwise, if we pushed here, maybe the load transferation is, we don't have any connection between this, so it's not appropriate. Displacement, and we're going to use roof. So this is about 180 millimeters. 180 millimeters. Okay, we can add here or here. I will take it back. And now we're going to this first floor using this one, and it's here. Quite okay. It's pin 19, which is off of the. Okay, and we are done. The next is meshing part. So there is one thing. If we want to compare the results with ETABS, we should give a large or a big or a coarse meshing. Otherwise, the results will not be similar. Because the ETABS, which we give the output is just a single elements. We didn't give any extra output, or we didn't divide or didn't measure these elements. So for this reason, I'm going to give a large mesh in the part here. I want to give 750 millimeters with a coarse mesh, which is almost similar with ETABS elements. Next is we can check the element. The element should be beam. It's beam, okay. And next we're going to mesh it. So the mesh is completed. Now we are going to the job and going to submit. But before, I'm going to check the directory theme. I'm going to use Pushover 180. Okay, now I'm going to submit it. Yes, it's the submission is completed successfully, and we can check monitor some to see if what's good. Yeah, the first step is actually completed, which is the gravity load applied, and the next step is that pushover steps. So it's quite finished quickly. because we give a large mesh. So if we give a small mesh, then it, so this is the results of we can check the active yield. So this part is yield, the brass is yield, and here. So we can go to back again and check step by step. And the first thing is we are going to find that first yield should be quite close with ETABS. Otherwise, our work is not good. Yes, here we go. In ETABS, because we applied in this region, so this brass deformed. If we apply this region, so this will deform. So the first thing is for us, this brass in the top bottom is deformed or yield. So this is quite logical, and we can go again to the result. Going to the result. Sorry, it's result. So going to back. So we can see it's 200. So I'm going to take the output. Going to the output, time history output. So we have reaction force, where we have two reaction force. I'm going to take the reaction force save as sum. So because we want the sum of this, I'm going to call RAF. And the next is the displacement. So we have two displacement. One is roof. We want to take the roof. So the roof should be as is. Okay. So this is it. Now I'm going to back here, and here is the parameters. The displacement. We want to find in this step time how much is the displacement. So this is the time steps, and this is the displacement. So this is 2, 2, 3 between these two, which is 22 to 28 millimeters. Now it is also completed. We're going to see again the pushover and first step. Okay. Now we can next. Yeah, exactly the same region. This point is back damaged. It's going to damage it. Yeah. The same, our structure is also damaged in both two brasses. This part is quite okay, and here is the parameter is between these three numbers, and the yield point is going to get from the code. Here is pushover curves, and we can see I'm going to open display pushover curve. So this is the pushover curve. The pushover curve. So here is the using seeing based on the ASC 41, we can see the yield point is 80 millimeters and with a maximum 3000 kilonewtons. So we can see this parameter is very close, very close to 20 millimeters, from 18 to 20 millimeters, very close. And next is in the same point, 223. We want to check the base shear force. So this is the base shear force here. It's 2500 2500 kilonewtons. That was 3000, and we can go to further steps. Yes, this is the further step, the next, which is the bottom point of this is here, going to the collapse prevention, this point and this point. So exactly we got the same here. Now we can quickly, I'm going to change, go to the assembly. I'm quickly going to change the these seats, because it's not I'm going to give from these parts to other parts. So displacement one is here, I'm going to select it here, and next is going to displacement roof, and it's here. Now I can check again to the load which is applied in this way. Going to back, I'm going to submit it again to get the proper results. The first step is completed. The second step is almost. Yes, it's done. Now we're going to see the results again, and it should be the deformation should be in this quite, yeah, because we push from this side, this deformation to this. Go to active, yield, and go to back. Yes. So so again the same location, yeah, again. So this is the results which we got from this pushover analysis. Now we can go to plot the force displacement curve. Here is the base reaction from the bottom, and I'm going to use sum of this we called RAF, and the special should be taken from the top of the roof. Save as. Okay, now here is the operation using combine, and it should be X and it should be force in the Y. So it's vice versa. I'm going to quickly change it. I'm going to delete these again. I'm going to operate this time combine, and I'm going to times -1, which is going to in a positive direction. So this should be inner right. Okay, so this is the results we got from pushover analysis. So the maximum load is almost to 5,000, which is this should be deleted. This should be, we can call, yeah, the maximum is almost to 4,005. So this is the results. We can edit this result in a Excel sheet like this, and so I can delete them here. Sorry, select C. I'm going to delete here, and instead I'm going to copy this data, copy and paste. So here is the curve which we got, the force displacement curve, which is the maximum is almost 4,500, and we can check in our, the maximum is almost 5,000. So this is the meshing part. If I reduce the mesh, use a coarse mesh, and I can get that point. If I use a large mesh, so the result will be less than, but totally the yield point is with yield displacement is quite similar. So this is the end of this tutorial. I hope you can learn something, and if there is any question, please put in the comments. I will find time and answer your question. Thank you for watching. See you next time.